me to come tonight, and I hope this is an interesting presentation. A little bit about myself. I'm an amateur astronomer, and I have several different telescopes that I use. I have my own domed observatory at our family farm, and a 14-inch Schmidt Cassegrain on an isolated pier mount there, so I can do some astrophotography. I've got 7 too many telescopes right now, according to my wife. So I do this kind of stuff, for fun. I have, whoops, it went away, didn't it? I let it sit too long. I gotta wake it back up. There we go, put that back. Do planetarium programs. I do some star parties for high schools in the past. The talk tonight that I'm going to give is about distances in the solar system and how to make these really immense distances a little more tangible. And hopefully give you some examples, and it'll be a participatory talk, so you'll all get to participate before it's over. My day job, I work at a small company called Honeywell, which has about 130,000 employees, and I'm in the aerospace group. I work on ring laser gyroscopes and inertial navigation systems. All of our gyros actually sense the rotation of the Earth and the orbital motion of the Earth around the Sun. So all of our test piers have to be oriented correctly to Earth's polar axis. So I also support our metrology department doing star sightings to make sure we have the heading correct, and doing all the computations with the data from the U.S. Naval Observatory. So it's a limited form of celestial navigation. And so I've taught some classes on that limited form of celestial navigation as well. So with that, this is what's out tonight. Unfortunately, the clouds are not cooperating. Otherwise, I would be talking about Mercury and Venus, which are about 4.5 degrees apart. So in the sky out there, it'll probably be too low by the time I'm done with my talk. But if it's clear on the next few nights, look out to the west. The really bright thing will be Venus, and the dimmer one will be Mercury. If you have just a pair of binoculars, like you take to a football game or something, take those binoculars and put them up to the sky, and Mercury will be a whole lot easier to see. Let's see, what else? Venus. By the way, the planets are really neat. Venus is always kind of low to the ground. I mean, it can get up pretty high sometimes. But when it's low there's a lot of atmospheric refraction. So when you're riding in the car, as you're driving down the road, you see all the mirages in front of you on the road. That's the same thing that's going on in the air, and that will make Venus twinkle red and green and white and red and green and white. And actually, a lot of pilots will call it in as somebody who's not on the radar, an airplane, a UFO, something that's there. But whenever Venus is low in the sky, morning or evening, a lot of people call it in as, this strange object that's stationary and not moving and things like that. So just be aware of where the planets are when you're out flying around, because sometimes they can fool you. Okay, so that's kind of me, and I'll give you a chance to ask questions later in the talk at the end, after you get to learn a little bit more about me and some of the strangeness that I bring. So this is a talk that I first gave in 1999. So 19 years ago is the first time I gave this talk. And there's a friend of mine, Tippy DeAria, who's an amateur astronomer in Florida that wrote books on how to collimate telescopes and did a lot to help create the Winter Star Party, which is a gathering of amateur astronomers in the Florida Keys. So I want to give him credit for the idea of this talk, but the actual implementation is stuff that I've done. So we're going to talk about the solar system, and we're going to talk about how to make these astronomical distances plain. I mean, people know miles. People know, 5,000 feet for the length of a runway. People know how far it is to drive to North Dakota, stuff like that. But astronomical distances get really tough. So what we're going to do is we're going to use a special paper, and each grid of this special paper represents 1 million miles on a side. And it's called Heliocentric Illustrative Tissue. So you can get it at certain special supply stores. And I have some here with me tonight that we can all use for doing this. And it's graphical, and we're going to use this to travel through the solar system. So everybody will get a chance to have their hands on it. So this is Heliocentric Illustrative Tissue, or HIT. Now, Tippy, the guy I borrowed the talk from, called it solar heliocentric illustrative tissue, or sun-centered example paper. So the extra sun is just, kind of bad, and the extra S makes it bad, so I just call it heliocentric illustrative tissue. For those of you who like acronyms, you can figure it out later. So we'll start with the sun, and we'll just give a quick tour through the solar system here. And I'm going to tear off one square of the heliocentric illustrative tissue. And remember, this is 1,000,000 miles on a side. And the sun is about 870,000 miles in diameter, about 900,000 miles or so. So I'm just going to fold the corners in if I can. This heliocentric illustrative tissue isn't cooperating very well. But something like this is roughly oblong, weirdly shaped, but about the size of the sun. So we'll take this piece of sun in heliocentric illustrative tissue and park it over here for now, and we'll come back to the sun. But the sun is mostly hydrogen. It's got a little bit of helium in it, and it's so big the gravitational pull is pulling that all down into the middle, and it's making fusion happen in there. And that fusion is putting energetic particles out to push the sun back out to the size it's at. And the density is about 1,400 kilograms per cubic meter. And so water has a density of about 1,000 kilograms per cubic meter. Did I do that right? Yeah, I think that's right. So, cubic meter is pretty big. That's 9 cubic feet. So, this is a picture of the recent solar eclipse. Did anybody see the solar eclipse this past August? Super. Pretty cool. So I drove to Nebraska and was in a little town called Tryon, Nebraska, and grabbed this image with my camera, and thought it was pretty cool. You can see some solar flares there and up at the top, and this is right at the end of the eclipse, and this is the beginning of the so-called diamond ring. So the diamond's there. So Mercury, so we want to travel out to the mean orbital distance of Mercury. It's not quite circular, so we're just going to take the average radius to get from the sun out to Mercury. So that's 36 million miles. So I need to pull off 36 sheets of heliocentric illustrative tissue. So we'll just do it by 6. 1, 2, 3, 4, 5, 6. And so 6 and 6 is 12. 18, 24, 30, 36. So we'll go here, find the edge. So now we have 36 of these sheets of heliocentric illustrative tissue. It's a little bit cold in here, so I'm going to make a scarf. Mercury, once we get to Mercury, is about 3,000 miles in diameter. Remember my sun here? So if we took a pin and stuck a pinhole in this piece of heliocentric illustrative tissue, that would be the size of Mercury relative to the sun. And Mercury really had just a couple of spacecraft fly by until fairly recently. The Messenger probe orbited in 2011, and that's the first time humans have had a probe orbiting Mercury and studying the surface of the planet. So there's no atmosphere on here. It's a rocky world. It's about 5.6 times the density of water. Its day to rotate once is 59 days, and its year to go all the way around the sun in one orbit is 88 days. So these two are locked into it. So for every 3 days, there's 2 years that go by. So it's very interesting, a 3 to 2 day to year resonance. So the planet after Mercury is Venus. And Venus is 68 million miles out, which means we need another 32 sheets of this stuff. So we'll pull off another 32 sheets. Don't worry, by the end, you'll all get to have some. 1, 2, 3, 4, 5, 6, 7, 8. So there's 8. And if we pull out another 8, we get to 16. Oops, I'm ripping it. And pull out another 8, I get to 24. Pull out another 8, and I get to 32. So there's my another 32 million miles, or 32 sheets. in Heliocentric Illustrative Tissue. So, Venus. Venus is a really hot planet. It's 7,500 miles in diameter. It's sometimes called the twin of Earth because they're roughly the same size, but it's a whole lot hotter. So things will melt on Venus. The surface temperature of Venus is close to 1,000 degrees. So to have a probe land on Venus, it doesn't last very long because none of the electronics will survive that kind of temperature for very long, and it's very difficult to cool something on the surface of Venus. So its atmosphere is carbon dioxide. It's one of those greenhouse gases. So Venus is very close to the sun, but it has a runaway greenhouse effect. But it's actually hotter than Mercury. So it's also got the most dense atmosphere of the inner planets. Not many probes have gone around Venus. It's difficult to see through all the clouds. And this is a Hubble Space Telescope image of Venus. So remember, it's the size of a toothpick. If I pull out my piece of sun here. So Mercury was a pinhole. Venus is about like a toothpick, a round toothpick. You have a hole in there. So now we'll go to Earth. Earth is, of course, 93 million miles out from the sun in mean orbital distance. So we need another 25 sheets of this stuff to get to Earth. So 1, 2, 3, 4, 5. There's the fifth one. 10, 15, 20, 25. So who wants to hang on to this journey to Earth? You know, we'll send it over here. There you go. Hey, I'm losing it. Need to loop this around a little more. So Earth, as we all know, is where we live. It's about the same size as Venus, so it's another toothpick hole in my heliocentric illustrative tissue representation of the sun. And it has no atmosphere. No atmosphere. No atmosphere. Anybody got a clue?
Nitrogen and oxygen, sir?
Nitrogen and oxygen, right answer. So, and a day on the Earth is surprisingly one Earth day. So I've been talking about days for the other planets in terms of Earth days. And so for this one, it's ourselves. And the year is 365.25 Earth days. So one little bit of trivia here. If you think it goes around once in a day, that's 24 hours. And you go 360 degrees in one day in 24 hours. Do the math, that works out to be 15 degrees an hour. But that's wrong. Because it actually also goes around the Earth, or the sun once in there. So it goes around 366 and a quarter revolutions in 365 and a quarter days. And if you do that math, that works out to be 15.041 degrees an hour. And if you forget about the 041, you won't have systems that navigate accurately. So all of the navigation systems, inertial nav systems, need to know Earth's real rotation rate. And for astronomers, that's also called the sidereal rate. So you'll see a star rise. If you have a good spot to watch where the stars are, like two buildings you can line up, you'll see a star rise about 3 minutes and 56 seconds earlier one night from the previous night. And that's the sidereal rate, and that's something you can observe yourself and see that we're actually rotating around the sun. So far, we're the only planet with open water. Mars. So everybody's been talking about Mars. Elon Musk sent his Tesla on the way to Mars. Anybody watch the Falcon Heavy launch? That was pretty cool. That was pretty cool. Most companies will put a concrete block at the top of the rocket for weight. Musk had the cool PR idea of, instead of a concrete block up there, which nobody cares about, he put his Tesla. So it's pretty cool PR stuff. So we need 49 sheets to get there, so we'll count by sevens this time. 1, 2, 3, 4, 5, 6, 7. And there's 14. There's 21. There's 28. There's 35. There's 42. That should be 49. 7 of them I did. Oops. Can't do math in my head anymore. Who needs the trip to Mars? Hell, come over here. I think you had your hand up first. There you go. Don't worry, that'll be enough for everybody by the time we're done. So Mars, when I did this talk 19 years ago, Mars had very few things there. The Spirit and Opportunity were the only rovers on Mars. The Viking landers had been there in the 1970s. And since I started giving this talk, all kinds of stuff has happened on Mars. This is supposed to be a view from the Curiosity rover of Gale Crater. Here's Mars and Earth in a size comparison. So Mars is a lot smaller. If you were in an airplane flying around on Mars, in the really thin atmosphere of Mars, you'd definitely see the curvature of Mars easily. Even being on the ground, you would start to see the curvature of Mars. So it's about smaller than the Earth, so it's about like a paperclip hole in my sun, my heliocentric illustrative tissue sun. It's got another carbon dioxide atmosphere. There's other stuff in there, but it's mainly carbon dioxide. And it's about 24 hours and 37 minutes. So the guys at JPL that are running these rovers operate 3 shifts a day on Mars time. So their time, human and Earth time, rotates a little bit every day. That would be a miserable thing. Go to work a half hour later every day, 37 minutes later every day. And it takes about 2 years to go around the sun. So Earth goes around in 1 Earth year. Mars goes around in about 2 Earth years. So every 2 Earth years, the 2 planets come close together in their orbit. And that's why you'll see missions to Mars occur about every 2 years. Because it doesn't make sense to send it across the sun to get there when they're going to be close together every 2 years. And that's also the problem for astronauts. If you're going to send an astronaut to Mars, there's a window to get them to Mars, and it's going to take 6 to 9 months to get them to Mars. And then it's going to be another year before there's a window that opens to get them back. So that's a really long time to be out there. And we'll do a thought experiment at the end about that. Jupiter. So now we need to go 344 more sheets to get out to 486 million miles to Jupiter. So I need help with this, so we'll start here. And if you just go take some and pass it back, send it on back to the room there, we'll just keep going. We'll get, we need to get about 344 more sheets of heliocentric illustrative tissue off of the spool. Yep, keep going. Keep going. I've had people make turbines with it. I've had people make arm wraps. People have made, just piles on desks. People have made slings for their arms. Okay, so hang on a second. Let me go take a count. Okay, I think we need 3 more sheets. So we have arrived at Jupiter. So the way I cheat is I know that this is a 1,000 sheet roll. So when you get heliocentric illustrative tissue, you can't just buy any stuff that looks like toilet paper. You have to get the stuff that has 1,000 sheets per roll. So now we're at Jupiter. And Jupiter is about 89,500 miles in diameter. So if you have a number 2 pencil that you use for exams, you take that number 2 pencil and you poke it through this heliocentric illustrative tissue version of the sun. That's how big Jupiter is. It's the largest planet in our solar system, and it's about 1,000th the mass of the sun, but it contains 2.5 times the mass of all the other planets combined. So it's pretty impressive. And that big thing spins all the way around once every 9 hours and 55 minutes. So if you're looking for the Jupiter, great red spot of Jupiter, if the clouds cooperate, you can pick it up on almost any night, except perhaps in the summer when our nights are really short up at this latitude. It takes about 12 years to go all the way around. So for those of you who know the constellations of the zodiac, that's the ecliptic path of the sun through the constellations in our sky. The planets also go along that ecliptic, and Jupiter moves about 1 zodiacal sign per year. So, anything else on Jupiter? Oh, it's about 1.3 times the density of water, and it's mostly hydrogen and some helium there, so it's almost a star, but it's nowhere near big enough to have the gravitational compression to create a star. It may have a diamond core, though, if we could ever mine it. So now we need to go to Saturn. Saturn is 894 million miles out. So we need to pull out another 408 sheets here. So we'll start on this side this time because these guys haven't had enough heliocentric illustrative tissue. We're not doing too bad on time. You know, I'm probably talking more than I should, but we'll time how long it takes our group to travel at the speed of heliocentric illustrative tissue. And then we'll do a rough calculation. This is good practice. You're making a ring, and if we can get the heliocentric illustrative tissue to make a ring all the way around the outside, that'll be like the ring of Saturn, and we'll all be sitting in the middle of the ring. A few people got that. Oh, cool. Yeah, here we go. We'll go close the loop. We'll go close the loop. Oh, the strand is broken. All right. Keep going. We need about 120 sheets left out of my 1,000 sheets. Here we go. We'll go be gentle. Get this over here. There we go. And we have a ring. We've achieved a ring around the group, and we're all sitting inside the ring. So this is great. So I think we need about 25 more sheets. We'll call it good. And we have now arrived at Saturn. So Saturn is the ringed planet. Have any of you seen the rings of Saturn through a telescope? It's pretty cool, isn't it? To see those rings there, it looks like a cartoon in the telescope. So Saturn is actually less dense than water. So it's about 75,000 miles in diameter. So if you think of a mechanical pencil, not a big fat one, but a thin one, and you take your heliocentric illustrative tissue representative of the sun and put a thin mechanical pencil through there, that's about the size of Saturn. It also rotates very, very quickly, about 10 hours, 40 minutes. It takes about 30 years to go around the sun. And these rings are just really complex, little specks of dust and stuff. They're very, very thin. They're only about, tens of meters thick, the whole ring structure. And it's just reflective, so when it tilts, we can actually see them here from Earth in our telescopes. Now, the neat thing about the picture there is this is a Hubble Space Telescope picture of an aurora in progress on Saturn. And that was the first time anybody had captured an aurora at both poles simultaneously. So we've since captured it here on Earth, but at the time, that was the only time we'd seen an aurora at both poles simultaneously. So now we get to go to Uranus. And we need another 900 sheets to get to Uranus. So we'll go send it out this way. And pretty soon we're going to run out of heliocentric illustrative tissue. Except that, in my briefcase, I have more. There we go. We'll keep going.
Sir, sorry.
Don't apologize for ducking under the heliocentric illustrative tissue. Yeah, absolutely. Be my guest. I'm very productive. You need more, you know.
Is that enough?
No, keep going. We got to get down to about 200 sheets left here. Okay, I think we're getting there now. So we'll call this good. So we have arrived at Uranus. And Uranus comes from a Greek root word, urano, which means sky. And so Uranus was the god of the sky in that ancient mythology. And people, astronomers who measured where the stars were and created a star chart, created a thing they called a uranometria, or metric of the sky, or chart of the sky. And so people who do that, who create maps of the sky, there's a few around today that still do it, are called uranographers. For instead of a cartographer, they're a uranographer for sky mapping. Not to be confused with a urologist, which is something completely different. All right, a few people got it. Okay, so Uranus. Voyager 2 has been the only probe that's done a close investigation of Uranus. So that was done in the early 80s when it flew by Uranus. It's about 32,380 miles in diameter. So if you think of like a wooden matchstick, and we go poke a wooden matchstick through my heliocentric illustrative tissue version of the sun, that's how big Uranus would be in the scale of heliocentric illustrative tissue. It's got hydrogen, helium, and it's got this thing called CH4. CH4 is strangely appropriate for heliocentric illustrative tissue. Does anybody know what CH4 is?
Methane.
Got it. Yes, it's methane. So, strangely appropriate for heliocentric illustrative tissue. So, its day is 17.2 hours, but it spins the opposite direction from all the other planets. We don't know why, but it does. And it takes 84 years to make one orbit around the sun. So we're getting way out there. We're almost about 2 billion miles out from the sun now when we're out at Uranus. And the next planet is Neptune. 2,182,000,000. We got to go another 1,000 sheets. So, lest you think I'm running out of heliocentric illustrative tissue,
Normal.
this side's been not getting much action. We'll start over here. You might want to stand up and just hold them back. Who knew you could have so much fun with heliocentric illustrative tissue? It's just okay, I think we're getting we're getting pretty close. So let's cool it about here. So 2 billion. No, we got to go more. Never mind. We're good. We're good. So here we are. We've now arrived at Neptune. Neptune is almost a twin of Jupiter. I'm sorry, Uranus. Getting myself mixed up. So Neptune is almost a twin of Uranus. It's about 31,000 miles in diameter. It's another matchstick. If I pull up my Heliocentric Illustrative Tissue version of the Sun, it's another matchstick poked through here. It's hydrogen and helium. There's no methane present on this one. It's there, but it's not in very high quantity. So it's got kind of a bluish color, 16 hours and 7 minutes for a day, and a year to go once around the sun takes 165 Earth years. So it's more massive than Uranus, but it's a smaller diameter. And Voyager 2, again, is the only close investigation, although NASA is talking about a future mission to go orbit Neptune and explore Neptune. So when I did this talk 19 years ago, when I first did it, Pluto was still a planet. And in 2006, it was demoted to be a dwarf planet. And so they've created some rules for planets, which I'll actually talk about later. So now we need to get out to Pluto. So we need from the New Horizons probe that shows that heart-shaped area, and they've named a bunch of these areas. And it was discovered by an American, the only planet discovered by an American, Clyde Tombaugh, discovered it from Lowell Observatory in February 18th in 1930, so more than 88 years ago now, since I did this talk a while ago. Atmosphere is actually found as nitrogen and methane again. The day spins about 6 days, 9 hours, 248 years to go around. And at 1,476 miles, it's the tiniest something formerly known as a planet that we have. And because it's so small, that's why it got demoted. So Pluto didn't care. Pluto hasn't changed, but our definition of a planet has changed. So prior to, remember this picture here, that's what it looks like from the New Horizons probe. Prior to New Horizons, this was the best picture we had of Pluto with the Hubble Space Telescope. It's that far away and that small. So the criteria for a planet, it must be in orbit around the sun. Yeah, Pluto meets that. The object must be massive enough to be rounded by its own gravity. It can't look like a peanut or something else like some of the asteroids do. So it's round, so it meets criteria number 2, so it meets the first 2 criteria. And it must have cleared its neighborhood, which Pluto hasn't done. There's a bunch of companions out there. One of its companions is another dwarf planet called Eris. And in Greek, they discovered Eris about 2005-ish, and that caused all the controversy that made Pluto get demoted. And so Eris was named because Eris in mythology is the bringer of discord and strife. And there was a lot of discord and strife about demoting Pluto to a dwarf planet. So what's next? If we were going to go travel beyond Pluto, what would be next? There's a thing called the Kuiper Belt, named after a Belgian astronomer. And outside of that is an Oort cloud, which is a Dutch astronomer, Jan Oort. And then there's all chunks of stuff out there. There may be other things the size of Pluto and Eris. Well, what about going to another star? So if we were going to go to our sun's nearest stellar neighbor, which is Alpha Centauri, the Alpha Centauri system, Proxima Centauri, it's about 4.2 light years away. That's the distance that light travels in a calendar year, an Earth year. Light travels 186,000 miles per second. So go turn that into how far it travels in a year. If we were going to go there using heliocentric illustrative tissue, we would have 25,000 rolls of 1,000 sheets each, with each sheet being 1,000,000 miles. So it's taken us about 35 minutes or so to, if I subtract the 5 minutes I spent yakking with you guys at the beginning, take about 35 minutes to go through almost 4 rolls of heliocentric illustrative tissue to get to the orbit of Pluto. So that means traveling at the speed of heliocentric illustrative tissue to get to Alpha Centauri, we would be sitting here for about 6 months doing nothing but spooling off toilet paper. Depending on where you source your heliocentric illustrative tissue, just the supplies, just the toilet paper for the mission would be about $17,000 just to buy 25,000 rolls of heliocentric illustrative tissue to do a demo. So now think about sitting here in this room for 6 months spooling off toilet paper. Our brains get fuzzy because there's nothing to do but spool off toilet paper. We don't get much exercise because we're locked in this room here. So think of what an interstellar trip really means if it's that much effort to get there with heliocentric illustrative tissue. The stars are really, really far away. So that's kind of the end of my talk. I was going to talk about the planets tonight a little bit, but I'll take questions about this first, and then I'll pull up. We'll switch to Sky Safari Pro and run some simulations of the sky if you would like to, or if my time is done, we can wrap up. Any questions that I can answer for folks? Yeah.
Do you know at what point a celestial body becomes a sun?
Well, that's a good question. I don't have the firm definition tucked away in my gray matter, but I think it has to be massive enough that it creates fusion in the core, such that there's light that's coming out of it. So some objects can just be hot and massive, but there's no fusion going on. So they might look like a brown dwarf. So they're not really pumping out a lot of light. They're pumping out a lot of infrared energy, but those would not be a star. But I imagine that Wikipedia would probably have a good definition if we wanted to go get on Wikipedia and look it up, better than what I have in my memory, my gray cells at the moment. Next question. I'll go work my way around this way. You, sir. Yep.
So, is it possible to have a star that works on fission?
No, it really isn't, because there's nothing to get it started, and that makes stuff, fly apart, and so the gravity needs to be there to make the fusion. Fission depends on heavy metals, and these heavy metals like uranium are only created in a supernova. When a regular star blows up, it's got those heavy metals there, and those heavy metals then get distributed, and they eventually get concentrated in planets like Earth and Mercury and the Moon, things like that. Tuck the heliocentric illustrative tissue out of the way. Yes, in the back there.
Why would Jupiter have a magnet?
So there's a lot of pressure there, not enough to create a sun, but if there's any carbon in there, that'll go sink to the middle, and then that pressure will compress it, just like artificial diamonds that we create around here. You.
So at the current, advancement we have in our rockets, how long will it take us to travel to the sun?
To the sun, 93 million miles. Mars is about 40 million miles from us when we're at the closest point of approach. It takes us about 6 to 9 months to get to Mars. So if there'd be a gravitational well helping pull you into the sun. So it's probably about 9 months, 6 to 9 months. That's my guess, just by doing the logic I just did. So I don't have a firm answer, and that's not necessarily the right answer, but that's the logic I use to come up with somewhere in the 6 to 9 month area. Sure.
So in the old definition of the planet, wasn't it that the planet had to have an atmosphere?
No, it was never about an atmosphere. It was about just shape and size. And in the 1930s, we didn't know that there was this Oort cloud or Kuiper belt. We didn't know that there were going to be other things the size of Pluto out there. Nobody had seen them. Nobody had even postulated that they existed. And so it only became a problem when we found another item, another object that was roughly the same size as Pluto. And the theory was that there'll be maybe tens or hundreds of them out there. So now all of a sudden you run the risk of, instead of 9 planets with Pluto? Do we go down to 8 and have a bunch of dwarf planets? Or do we start saying, oh, we have 10, 15, 20, 30, 40, 50 planets in our solar system? And pretty soon everybody loses track of what a planet is and what it isn't. So it was just a choice of us humans to make a definition to classify things. We're really good at trying to classify stuff. And sometimes we classify stuff when we shouldn't classify it. And sometimes we classify stuff and it's helpful. So hopefully this planetary thing was a helpful thing. Sure.
How do you know it will take 6 months to go around the room?
So what I did was, to do that, I looked at the distance to Pluto, which was about 3,800,000,000 miles, 600 million miles. And I said it took us about 35 minutes to travel that distance. And so I said that's about, 11 times the speed of light or so. Rough rule of thumb. I just pulled out my calculator and did that. And I said 4.2 light years. I converted that into billions of miles. And each roll of heliocentric illustrative tissue is 1 billion miles. So there's 25,000 billion miles to get to Alpha Centauri. It took us 35 minutes to go through 4 rolls. I can see that it took about 4,000 hours to go through 25,000 rolls. And I know that there's about 8,700 hours in a year. So half of that is about 6 months. So it's just unit conversion. So when you're doing math and unit conversion, you go inches to meters or inches to centimeters or pounds to kilograms. If you're putting fuel in an airplane, you want to make sure you know whether you're getting pounds or you're getting kilograms, or you're getting gallons or you're getting liters. So these conversions like that is what you do. So you just go convert from one unit to another. And you convert from light years to miles to rolls of toilet paper. Sure.
How far is it to the Andromeda Galaxy from the center of our galaxy?
So the Andromeda Galaxy is about 2.2 million light years away. So 2.2 million light years, and Alpha Centauri, which we were talking about, was 4. So if you take 2.2, call it 2 million to make life easy, divide by 4, you're talking 500,000. So 500,000 times 6 months is about where you'd end up. So, yep, sir, yep.
Has it been estimated when the sun will eclipse? It's on that.
Yeah, it has, and you probably don't have to worry about it in your lifetime. It should be about 4 to 5 billion years from now. Yep, go ahead. Yeah, go ahead. Yeah.
Why are some orbits resonant with other orbits or days?
That's a good question, and the answer is gravity. So actually, if we look at the Earth and the Moon, they're gradually changing as they go around. And the Moon used to have its own spin rate, and over time, the gravity of the Earth and the tidal pole locked it to Earth's rotation. So the Moon goes around the Earth in a month, but it always keeps the same face towards the Earth. So its day and its orbit around the Earth are the same exact period. So tidal forces tend to slow planets down and lock them together. So you get into these gravitational things where they lock into resonances, because if they get out of that resonance, one of the planets will get ejected and ejected from the solar system. So it's a minimal energy state to be locked into these resonances. I think you had a question over here. Did you have one? Oh, okay, all right, I missed it. Go ahead.
Is it because of the size of the gas planets that they have a faster orbit or rotation?
Yeah. So when they coalesced, everything is spinning. And if you watch a skater at the Olympics, when they have their arms out like this, they're kind of spinning slow. And as gravity pulls all that matter in closer and closer, and the skater pulls their arms and legs in closer and closer, they start spinning faster and faster and faster. So it's the conservation of angular momentum. And that's what's going on there to make those planets spin so fast.
I believe it's Pluto that has the ellipse orbit, like
yeah.
even.
Yep.
Is there any chance of it colliding with another planet?
I don't know the exact answer to that question, but not in the near future. So the elliptical orbit, we don't really know why Pluto, if it was captured as an interstellar traveler, or how it really ended up in that elliptical orbit. That we really don't know. But it's highly elliptical and inclined to the orbital plane in the solar system. So if all the planets were like in the plane of my hand here, Pluto is going to be tilted like that. So it's tilted and it's highly eccentric. So it's not circular. So it's a very interesting thing, and it's inconsistent with what the rest of the objects we call planets are. Yes, ma'am.
So if you were to send an astronaut to Mars, would you send them where Mars is going to be in 6 months, or would you send them directly at Mars?
You'd send them where Mars is going to be at the end of the journey. So there's a limited amount of thrust that we can put into a rocket, and so you have to use a transfer orbit to get there, and you got to conserve your energy. So if you aim for where it is now, you're going to miss it, and Mars will be, far gone. So you need to aim for where it's going to be and recognize that the sun is going to be pulling you back while you're at it. So you need to start off one way and your trajectory is going to curve, and then Mars is going to probably be moving a lot faster than you are, so Mars is going to catch you as you get out to that spot. So maybe just a couple more questions. Yeah?
Do you have any idea why all the other planets except for Pluto are on a plane? Because to me it doesn't make much sense that they all are going in this one circle that is all flat.
Yeah. So if you go, in fact, if you go to Wikipedia again, there's got to be an article. I don't know for sure, but there should be an article on what's called a protoplanetary disk. So as a star forms, there's all this material around this gas cloud, and it gets gravitationally bound to this sun, which is the most massive thing. And that whole disk is rotating. So as stuff comes in, it's rotating, and it turns into this flat disk just to conserve angular momentum again. And so gradually everything spins around the axis of that heavy weight in the center, which will be the star. And so they've got images of a few protoplanetary disks, and you can see that things are starting to shape up like that. That's why most of the planets all spin the same direction as well. Now, Uranus was one of those weirdos. Was it Uranus or Neptune? Now I've forgotten. But one of them is spinning the wrong way. And that's a mystery as to why is that thing spinning the wrong way. We don't really know. But everything else is just conservation of angular momentum. Goes back to that skater analogy again, pulling in the arms. Yeah, you haven't asked one yet, I don't think.
Sorry, never mind.
Okay, go ahead.
Since Voyager 2 was so far out, did it hitchhike a ride in another probe?
No, Voyager 2 actually got gravitational assists from Jupiter. So as the planet is going along, the probe is if the probe is going along, the planet comes along, and then the planet drags the probe with it, and then they fire the thruster to go out this way. And so they've got an acceleration from the gravitational pull of the planet. And so you can go look at some of the, probably Wikipedia again, if you go to the Voyager 2, they can talk about the gravitational assists that it got on its way out of the solar system. So let's go for one last question. Anybody had not asked one yet that wants to? Cool. I guess it's your turn then.
Do you know if we have anything to defend if let's say asteroids coming toward Earth? Do we have anything to protect Earth from that?
No, we really don't at the moment. There's lots of ideas in science fiction that are out there. Some of them may or may not be practical. The biggest thing is to detect it and make a prediction with orbital mechanics of when we think it might have some interaction with Earth, and then figure out whether we need to do something about it. And hopefully we have 20, 30, 40, 50, 60 years of advance warning. Stuff that we haven't found yet is going to be fairly small. It'll create a lot of damage, but it won't be a planetary killer. Most of the stuff that's big enough to be a planetary killer we think we know about. But small stuff that can destroy cities is still out there. Small stuff. So that's kind of my talk. I can go show you some of the sky tonight if you want, but I've got about 3 or 4 minutes left. Mercury and Venus have set, but keep an eye out for those in the future. And somebody had talked about doing an astronomy night sometime, and I'd be happy to come back and and bring some telescopes with me if we wanted to do that when it's a little bit warmer out. So I think that's all I've got. Thank you for your attention, and I hope it was useful, informative. You learned something, and it was a little bit fun. And you can see that I'm not entirely serious.